Happy New Year, everyone, and I hope you feel refreshed. I do in the sense of hobby electronics projects. I get some closure on a lot of things, including this one. The 2nd of January, it might look like I'm a little late, but we're 10 hours ahead here in Australia, so for most people in the world, it was actually New Year's Day. Hi guys, this is part 2 of my time splitter, atomic clock, frequency counter, astronomy clock, core memory project. So let's power up and I'll talk you through what happens with this automated setup that it goes through. It's mostly a continuous shot, but it's broken up so I can talk you through it. Were I to just film this sequence and upload it, it'd probably take a little over 4 minutes, but it wouldn't really explain anything that it's doing. The first thing you'll see happen in a moment is it reading in its data from the core memory module that was saved from the last power cycle. You might see the reflection of a green flashing LED in the paper on the top right hand corner of the screen. That is an indication of the serial transmission from the core module to the astronomy board, and in my wisdom I mounted the LED at the back of the core memory module, but I'd normally see that reflected off a wall. Next we'll see a visualization of 64 bits being shifted into a grid. The resulting image when all 64 bits are shifted in is a visualization of the bits that were set in the core memory module. The 64 bits are interpreted as a pair of 32-bit floats that represent a latitude and longitude coordinate pair that was saved last power cycle. This location that was saved last power cycle is now called the default location because it will be used if the unit can't get a GPS fix for this power cycle. Now I might already have you scratching your head. Hang on a minute, it's not a shift register. That's not how core memory works. It doesn't get rotated from one location to another. Core memory is a two-dimensional matrix addressed across two axes with current driving lines to set or clear cores, depending on which direction the current is driven. Why would someone with enough motivation to write a true matrix addressing representation for a video write a shift register representation for the actual project? Well, the answer to that is that the astronomy board that's drawing the display is not the actual core controller. The core memory has its own controller. Data from the core controller is actually shifted out serially to the astronomy board. This facilitates minimal wiring connection to the astronomy board, but more importantly I can play with the core memory with a simple serial terminal, and that made a better demo video when I did it. If we look at a similar fanciful display of what's going on inside the core memory controller, and this time it is untrue, the data is read into a 64-bit array of RAM, and then that RAM can be serially shifted out in either direction, either out the front or the back end of the array. The core memory controller doesn't know that these are floats, it's just 8 bytes of data, nor does it have to. It's only when it gets to the astronomy board that it's interpreted as floats. Shortly after the GPS has acquired the time and date, it will set the clock. Notice that the time on the blue 7-segment display hasn't been set yet, that's just a running counter from power up. When the astronomy board sends the time and date to the clock board, the time will be announced. Like that. So now the clock board knows the time and the date, but it's not actually synchronized to GPS with regard to pulse per second input. All this time the astronomy board that's connected to the GPS serially is looking at the number of satellites received and the estimated accuracy of the position fix. It tries to save the most accurate position even if it wasn't the last position that was received. I'm not sure how this will turn out on video because you'll have to move your eyes back and forth very quickly to see it, but the clock is actually set a partial second ahead of the astronomy board deliberately. The clock board is waiting for a command from the astronomy board to sync to the pulse per second output from the GPS that the clock board is directly connected to. And that's what just happened. Setting the clock board previously a partial second ahead allowed the room for it to reset its second to sync with the pulse per second from the GPS. It should be noticeable that the GPS pulse per second output LED on the right of the screen is not in sync with the blue clockboard pulse per second LED on the left of the screen. That is, at least until the sync command is sent from the astronomy board. This is not a GPS disciplined oscillator. Once that happens, I'm trusting the rubidium time source to run the clock and ignoring the GPS from then on. This time lapse shows that there is still inaccuracy between the two. The red trace is pulse per second from the clock and the yellow trace the same from the GPS. When I recorded this time lapse, I added one count to the hardware timer that counts up seconds every 250 seconds for the timer that is running on the microcontroller, just to keep both traces on the screen. I assume that it's the GPS module that is the least accurate here because it has a self-survey mode that I'm not running. I think that actually takes hours or a day. Or you can also provide a fixed position if you know your accurate location, which I don't. You have to do one of those two things to get the quoted accuracy out of the GPS timing as specified in the datasheet. Speaking of location, this demo is as real as it can be for YouTube, but of course I don't want to show the whole world my true location, so I've had to pull a little trick that I also did when I was doing the mapping GPS. All that really entails is coming up with a couple of random offsets which can be positive or negative values, and then add that to the GPS values before your program does anything with them, especially display them. In this case, the offsets are only fractional, so we're still in my city. Now that the astronomy board is happy with the GPS location and the accuracy of it, it'll write that to the core memory module for the next power-up, in case it can't get a GPS fix on the next power-up. Note that when the astronomy board is writing to core memory, the graphic representation rotates off the top of the display. Now that we have a location, that's where the digital compass comes in. It starts cycling through a bunch of cities, beginning with Australia because that's where I am, and it tells you the basic direction on a compass, also a higher resolution bearing printed on the display, as well as a distance. The basic 8-direction LED compass assumes that the top is north, or that the user would be facing north looking at it. The capital cities of Australia get the fancy LCD spin transitions. After that there's some minor Australian cities, and the unit just gets faster and faster as it cycles through some world capitals. When the unit indicates that it's using a GPS location for astronomy data like that, it means that it's using the position fix that it acquired in this power cycle to calculate the astronomy data from there on in. It's going to apply a plus 10 hour time zone offset, which is true for Eastern Australia, and that applies to all times displayed on the 7-segment display or the LCD display, including astronomy values, sunrise, sunset, moonrise, moonset. Both the astronomy board and the clock board have a software calendar, so they can both wind back or forward a whole day and know the correct date, days of month, etc. And for the astronomy board, this is the cycle that just gets repeated for the whole time it's on for the rest of the power cycle. Just sunrise, sunset, moonrise, moonset, illumination percentage of the moon, and the time and date, and then it'll start that again until you turn it off. If for any reason the clock board is set to a different time with DTMF codes, the astronomy board will ignore that. It's receiving serial data from GPS. Just going back to the frequency counter, this segment demonstrates changing the gate timer value from 1 second to 1/10 of a second using a DTMF code. With 10 MHz input for demonstration, the counter will count 10 million cycles in 1 second, or 1 million cycles in 1/10 of a second. If you'd like to hear speech announcements at proper volume, there's an older video on my account for that. The unit uses Roman Black's 1-bit algorithm for sample reproduction. An 8-bit PIC reads the sample data from EEPROM. And this is the pesky SMA connector and socket, preventing me from lowering the core memory module into the position it's supposed to be. I do have SMA sockets that point straight up, so it would be easily possible. When I say easy, easy in theory. Well that concludes that, and I'm kind of glad the videos are out of the way because they were hard to make. I noticed I got a few subscribers out of that, and some of you probably to be notified of this one, so I hope you enjoyed it. And we'll see if you stick around. See you next time.